All right, we're back. And we're looking for a question from fall 2020. Something about a mechanism. Let's see, is our sound good? Sounds good. So we got this reaction. Oxymercuration. So we have any requests to do any of these mechanisms? This is version 1. Got another one here. A lot of mechanisms. In version 2, it's got some other mechanisms.
Do you think it's like could we just do part one from the begin, like from version one, like the first one that you went through?
Sure. Right here?
Yeah, those.
Okay. Just got some synthesis on here. Let's try it. Oh, I messed up. I wanted this one. I'm waiting for it. There it is. Okay. Fall 2020. Test 1, part 1. Coming right up. Here we are. Test 1. Fall 20, test 3. Part 1. All right. So we're starting with 4-methyl-1-pentine. So we have to know nomenclature of alkynes for sure. So we got an alkyne between carbons 1 and 2. That's what 1-pentine means. 3, 4, 5 with a methyl on 4. We're starting there. In step A, we're going to react with HB-Sia2 and use hydrogen peroxide and KOH in a second step. And you make HOB-Sia2. Now I'm giving you one of the products for the acid-base reaction that's talked about here. Right there, there's a reactant and a product. And we have to figure out what's going on. What's product 1 anyway? So we have to learn that during hydroboration, what you do is a Markovnikov. Yes, some of you have learned, oh, hydroboration is going to give an anti-Markovnikov reaction. No, hydroboration is a Markovnikov reaction with the more electronegative H, electronegativity 2.1, going on the more substituted carbon at the same time as the less electronegative B, 2.0 is its electronegativity, going on the less substituted carbon. That's a syn addition. There's no triangle, both bonds at the same time. So in step 1, might as well break it down. We're reviewing. Step 1 makes this species here with the less electronegative B on the end, R2, R equals Sia, sec isoamyl, sec isopentyl is the same thing. And on the more substituted carbon, we got the H. Markovnikov addition, syn, and we get that. And in step 2, you replace the B with an OH in an oxidation mechanism. An OH attached to an alkene is called an enol. Enols undergo tautomerization, and they become aldehydes. In this case, aldehyde because it's on the end of the chain. So product 1, what you're looking for, 1, 2, 3, 4, 5, product 1, and it has an aldehyde right there. There's product 1. And there you go. Draw a stick figure. I did a stick figure. It's right there. And during step A, mechanism that makes product 1, there's an acid-base step that makes Sia2BOH. What is closest to 5 pKeq for this step? So we kind of have to know that mechanism. And that reaction, what happens is an RO minus. That's a different R than before, so I'll just call it R prime O minus. Grabs the H from HOB Sia 2. And you get ROH, alcohol. And it's actually an enol, but we're going to treat it like an alcohol because we're just learning this stuff. And you get B Sia 2. And we're told the pKa of HOB Sia 2 is 10. You're given half the information. You've got to remember that alcohol has a pKa of 17 or 18. And pKeq is going to be -8. But that's not the question, is it? KEQ is 10 to the 8. Strong driving force for this reaction. And closest answer, oh, it's close, huh? Because 10 to the 10th is off by a factor of 100, and 10 to the 15th is off by a factor of 1,000. Well, 10 to the 10th wins. And if we chose 17 for our alcohol, I think it would be even closer, right? -7. We'd go, 10 to the 7. Then it's closer to that number. Oh, it's tough. This is a tough little question. I might be convinced to accept 2 answers here. I may have done that. I didn't read my key that well. But for now, if I use the numbers I did, I would pick that answer. And product 1, we drew a stick figure. Which base would give the observed result in step B? Well, step B, some base is taking an H off of here. pKa is 25 because that's a terminal alkyne. And we're making potassium isopropyl acetylide, which is wrong. Interesting. Did I count wrong? 1, 2, 3, 4, 5. Yeah, this is the right molecule, right? 1, 2, 3, 4. Ooh, didn't catch myself. Nobody caught me? That's a nice butyl group up there, isn't it? Yeah, you can name alkynes. You say this is acetylene. If it's an anion, it's acetylide, and name the group attached to it. And that's another way to name alkynes, isn't it? All right. But the thing is, you're taking the 25 off with some base that becomes an acid. The conjugate acid of the base with a pKa equals 35. It's the only number that works. Oh, that's not the number that works. 30. What's 25 minus 30? That's not working. I have some bad math going. I need the left acid, 25. Why don't I do it this way? Minus X equals -15. And I believe X has to be 40, right? So the pKa here is 40. Okay, 40. So I need the conjugate base of an acid with a pKa 40. The only pKa 40 that we know is an amine. So its conjugate base would have an N minus. And the only one I see with an N minus is potassium methanamide. And you'll notice over the semesters, these answers don't change. I just change the numbers here, and that changes the answer. Okay. And then product 2. I'm going to take this thing, the blue thing, and take its H off with the base to make potassium isobutyl acetylide, and then isobutyl chloride is going to react to make product 2. Isobutyl chloride looks like this. So that's going to end up on the other end of the alkyne. Product 2 has this. And then the new bond, I'll put it in green, to the red CH2, 1, 2, 3, V. There's your isobutyl. That is a carbon right there. Just make sure we know that's a carbon. And we want a stick figure. That's it. Be sure that's it. Product 2, circle it. And product 3, what happens to an alkyne, an internal alkyne, means it's the middle of a chain, when we react it with borane and acetic acid? That's one of our methods of making a cis alkene. You must know how to make a cis alkene from an alkyne and how to make a trans alkene from an alkyne. They're fundamental reactions for this test and future tests as well. And 1, 2, 3, V. And that is the answer. Make sure 2, 3. I went 4, didn't I? I went 4. So bad. Shame on me. I already had 1 drawn. Carbon 1's drawn. 1, 2, 3 with a V. That's product 3. And sin. So I'll put a circle on it. And we clearly indicated it as cis geometry by showing both of these bonds down. And draw a stick figure for one enantiomer that is formed of product 4. Be clear with the new stereo centers. Okay. What happens during OSO4 with an alkene? That's the question. There's alkene. OSO4 and tert-butyl hydrogen peroxide makes a what's called a vicinal diol. Product 4, I'll do it down here. So everything's gone blue. Go blue. And you get new bonds to OH. Notice I copied my carbons with the same geometry they had before. Pi's gone. And this is another example of syn addition. So you're showing me, the OHs go on the same side. So that's one of the enantiomers, and it doesn't ask for the other. If it did, that'd be easy. Copy the blue piece, put dash for each bond to OH, you have the enantiomer. I might ask you that. Who knows? I'm thinking, I started this test already. I'm thinking maybe I did. Ask for both enantiomers. Why not? Didn't ask here, so I won't put it here. I don't want to mislead you. All right, so I think we did 1 through 6 here, didn't we? Okay. So think about what we want to do next. Got any ideas right now so I can get it set up?
Maybe part 4, Professor.
Yeah, part 4 on the same exam. Which
this one on the other version.
Let me see. The other version, V2. V2 we got over here. There's V2. And part 4, which one do you like? Go down.
The second one.
Yes, good. Hydroboration. It's our biggest mechanism on our test. See, 10 points is huge. And I'm not mincing words. It's going to be on your tests. Either you're going to do hydroboration with an alkene, as we do here, or with an alkyne, and the first 8 points end up being the same either way. So you've got to learn this one. So when we come back, we're going to do version 2 of fall 2020 test 3, question 2. And I'll see you in about 5 minutes.